Hey, what's up, guys? This is Cheng here. So today let's take a look at the last problem of this week's weekly contest. Number 1595, minimum cost to connect two groups of points. I think this is a good hard problem, you know. I struggled a little bit. Yeah, I struggled on this. So basically you're given like two group of points where the first group has size one point, and the second group has size 2 points. I mean, the group size of size one is greater than the size two. But I think this is kind of not that relevant. But okay, let's just put it there. And then you're given like a 2D cost list here, which the cost ij means that to connect the ice node, the ice point from the first group and the j's point from second group, what's the cost of that? Okay, and then it asks you, right, to connect. Basically, our end goal is to connect any for any group from each side of the group. It has to at least connect to one of the other groups. Okay, so which means like let's say if you connect one and the first point on the second first group and the second first point on the second group, then both of these 2 points, I mean, are connected. Okay, and it asks you to need to find out the minimum cost to connect the groups, which means to connect all the points of each to the other group. Okay, so for example, the first one, right? The first one, we have basically we have these four options here, right? And then the best strategy is basically to connect one to A and two to B. Okay, so and the total cost will be 17. And example two here, right? So we have like many ways of connecting that, right? It's gonna be a 3 times 3 times 3, which is gonna be a what uh 27 possibilities, right? And then among all those of 27 possibilities, we use this one. So the best way of connecting is this one, 1 1 1 1. Okay, cool. So I mean, this is like kind of like you can think of this one as a DP or like a DFS, right? And basically, the DP, the top-down DP is actually is essentially a top-down DFS. Okay, and this problem is exactly that one of those problem, but uh, to be able to use DP, okay, you need to have like this kind of DP status, right? The DP here. So you need to maintain like two the state of the state of the status of the current state. So in this case, the state of the current status is what? Is the is how many basically is the connected points of from group one plus the connected points from group two. Okay, basically at this point, I mean, what are the connected points on the first group and what are the connected points on the second group? Okay, those are the I mean the 2D the two status of the current DP state here. Okay, but the difficulty for this for this problem is that I mean it's a list basically, right? The first group the first group and second group they're all a list. Let's say we have a the first group is this. We have a 0 1 2 3 4. That's the first group, and the second group is this, like 0 1 2 3. Okay, we need to find like a way of basically to efficiently store the current state of the connected status of all the points here on those two groups. We cannot use set or list. Why is that? Because you know, at least in Python, right? At least in Python, if for the top down, you wanna if you wanna like store that key, uh, basically you cannot put either a set or list into a hash table because it's not hashable. It has to be a has to be a primitive type like the integer or a top or something like that. So that's the basically the a little bit difficulty for this problem. And to be able to do that, uh, if you scroll down here, you check the size. Okay, you see the size is 12. So what does it tell you? It tells you that it's within the 2 to the point of 32. Okay, that's the length of the group here. So which means we can use a bit mask. Okay, we can use a bit mask to tell us which one. I mean, uh, if this point is connected or not. So what does it mean? It means that let's say we have this 5 points here, right? So which means at the beginning, right, everything is 0, 3, 4, 5. Okay, so it means that if the first point is connected, then we just change this one to 1. Okay, and then if the third one is connected, we also change this one to 1. Okay, basically we just use a bit mask so to compress a list into an integer, and this will basically we can use that one to track that. Okay, so that's how we track the connected points. And now what's our strategy? Okay, so what's our strategy of connecting the points here? I mean, a brute force way is what we can try. Mm, Obviously, we have to from group one, right? We have to try to connect each point to all the points on in group two. Basically, we need to try all the possibilities. Okay, which means, for example, this one for one, for for point one from group one, we have to try to connect to A, B, and C. Okay, once this is done, once we have tried all the possible ways there, that we need to move to the uh, to the point two here. For two, we also need to try both A, B, and C. For three, also three. We also need to try both A, B, and C. And so for the first, I mean, this is the second. Basically, our first status of the DP here is the status of the first group of first connected group. I mean, since we are trying all the possible way scenarios for from group one here, I mean, we can simply use the index to track the status. Basically, the index I means here from 0 to I, we have connected all the points. Okay, because once we finish connecting the current point, we're gonna move the I going forward to from I to I plus 1, so that I mean a single integer I here can represent the state of the first group, which means it's already been from 0 to I, all the points have been connected, and from I onward, nothing has been connected. Okay, so that's the first the group. And then in terms of the second group, right? For the second group, we don't know because we're trying all the possible ways, right? Because one can connect to either A, B, C, or two same thing. That's why for the second group here, we need to use a bit mask. Okay. Basically, every time when we decide to connect the current I to either A, B, and C, we're gonna set the bit mask of the second group accordingly, so that we this bit how basically this is how the bit mask is being used here. And once the no once the I reach the end of the first group, okay, it means that okay, so everything from the first group has been already connected to the second group. Now what's next? and we just need to check if there's anything that in the second group that has not been connected, which means if anything from the second group if has like the bit mask equals to 0. Okay, so for those points, we don't have to try all the possible what we don't need to try all the possible connection with 1, 2, and 3 here anymore, right? Because we know because we don't know because we don't care about the group 1 at this moment because all the points at group 1 they have already been connected. So all we need to care it is ourself basically. Okay, so basically at this moment the best strategy will be let's say for example if the after I reaching the last position of the group 1, let's say if B is not connected, then all we need to do is that we just need to find what's the minimum cost. What's the minimum cost from B to connect to any point in the group A, right? And we just need to use that one. We just need to use the minimum cost to just to connect the B to the first group. And to do that, we just need to do a pre-process. And we're gonna do a pre-process based on the cost. So we're gonna have like a minimum cost 2. Basically, 2 means for the group 2. This here it stores all uh, the minimum cost for each of the points in group 2 that connect to the group A. Okay, cool. Yeah, I think that's that. All right. Uh, all right. Okay, let's try to code these things up here. Okay. Mm, so mm, so first we need a size 1 here, right? Size 1 equals the length of the cost, and size 2 equals the length of cost 0. Okay. And then like I said, we need to pre-process the minimum cost to connect each point from group 2 to group A. Okay, so that to be able to do that, I'm going to do a cost 2 here equals to system max size, and the size will be size 2. Okay, and then for J in range size 2, for I in range size 1. Okay, basically I'm doing a nested for loop here. So for each of the group, for each of the point in group 2 here, I'm going to loop through all the points uh, from group 1. I just need to I'm getting the minimum among those. Okay, so here's going to be a J here, right? Cost 2 J and the current cost I and J. Okay. Yeah, so that's the pre-process, and then like I said, we're gonna define like the DP here. Okay, like the DP. The first one is the I. Okay, that's the index. Second one is the mask. Okay, and here in the end, we simply return the DP 0 and 0. Okay, so 0 means at the beginning, all the points have the bit value at 0. Okay, so I mean since it's a top down, I'm gonna use like this like the cache helper cache setup here in the Python. So this thing it means that I mean it will automatically returns the values whenever it whenever it sees the same input, the same ion mask. So basically, this one is equivalent to like manually maintain like a memory, the memorization hash table. Okay. Yeah, basically this is just like a shortcut of doing eliminating a few lines of code here. You can of course manually maintain a memory hash tables. I mean, it's fine. I'm just taking a shortcut here. So, and mm, like I said, since we're gonna have like two scenarios here, right? The first one is that I is is smaller than the size one. Okay, so this here means that I mean we're still connecting, we're still in the process of connecting the points from group one. Okay, then the answer is okay. Yeah, sorry. So like I said, the answer is max size. Okay. Uh, yeah, and this one is minimum of the current answer plus what? Plus the uh so we have connected the current one. Sorry, here. So to be able to connect to the current ice point, we need to loop through all the points in the group two here. Okay, size two. And yeah, here it means that at this moment, right, we are connecting the j's point from group two with the ice point in group one. Okay, and the I plus one means that we have already connected the current ice point. But how about the bit mask here? So for the bit mask, the way we're doing the mask is we are marking the j's point, the j's position in the bit mask to one. Okay, so here it's going to be how do we mark that? We just do a OR with the mask, and the value of the j's is to mark the j's one. We have to basically move one to the by j position, right? So here I mean, let's say we have 0 0 0 0 here. I mean, in order uh to mark this position to one, how do we do it? We need to do we need to get the values of 0 1 0 0. Okay, and then we do a OR. So how do we get the value of 0 1 0 0? We just need to move this the j by two here. So basically this one will become this one. Okay. We do a OR because we don't want to affect all the other bit values in the original mask, which means only the value in one here will become one here. Okay. Yeah. And it's also possible that I mean the mask though here it's already one. It's already been marked to be one, but it doesn't really matter. So one or a dual bit or is also one. So we don't care. We just try to set this one to one. Cool. And then don't forget to add the current cost. Okay. So the cost is the INJ. Okay. So that's when we try to set up connect the current ice point. Okay. Else, what is the else? Else means that uh, it's not actually else. So this is like the normal case. Basically, the else case is just like the base case. Okay, so what's the what's gonna be the ending point, the base case? When should we stop this DP, right? I mean, for a DP, you always need like a base case. So the base case is we have connected to all the points from group one. So the base case is this. The base case is when if I is equals to the size one. Okay, you know what? Actually, we don't need this anymore. So let me just do this. So when I is equal to the size one, then we know we have connected to all the values, all the values from all the points from group one. We just need to check if there's any points in the group two that has not been connected before. So how do we check that? We just need to check if there's any point, any bit values in the mask that still has zero. Okay, so let's do a for j in the range of size 2. Okay, so the way we're doing the check is that uh, similar like the or here. Now we just need to do an and here. Okay, basically, if because if any part if any bit value is 0, it means that the total value of that is also 0. Okay. Uh, Let me think. Mm, yeah. So basically, to be able to check if this current value, the current bit position is 0, we need to do this. We need to do a like the mask, do a and like what same thing here. Okay, equals to 0. Okay, then it means that that position is like is 0. So why is that? Because let's say we want to check if this position is 0 or not. So how do we check? We need to get 1 0 0 0. Okay, this is what we get from this move this the one uh bit movement, right, to the left by 3. So why is that? Because at this moment, right, only the everything else except for the current bit is it's definitely going to be 0, because we know once we move this, the all the other bit values, they're all 0. So it means that whenever we do an AND here, there will be all 0 here. Okay, so the final result of the last j bit position, they're all 0. And now we're only checking if the 1 here. So now the bit value we want to check is have the other part is 1. Now we just need to check if the mask is 0 or 0 or 1, because if it is 0 and then everything is 0, then the value is 0. It means that okay, so that that bit value is 0. If this is 1, it means that in this case it's going to be 8, basically, which means it will not be 0. Okay, that's how we use this bit mask to set the value and also to check the value. Okay, just remember this. It's a very useful trick here. Okay, so and at this moment, okay, we know the J's point has not been connected before, so we just need to return the answer. Yeah, we just need to return. Oh, I think. Oh, sorry. Okay, so here, let me do the return here. And we just need to return the actually, so okay. Can I do an answer here? Like I'll do answer 2 here. You know, the answer 2 is 1. It's 0. Okay. Here, since we're going to accumulate, right? We need to accumulate that answer 2 plus uh, the minimum cost 2 of the j. Okay. And then here we just simply return the answer 2 here. Yeah. So that's the base case basically. Whenever we reach the I here, now we just and now it's time to return. But what value we need to return? We just need to return the the rest points, the rest cost from connecting the the unconnected points from the group 2. Yeah, yeah, I think this should just work. Let's try to run the code here. Oh, sorry, cost 2 here. Cool, accepted. Let's try to submit it. Yeah, so it's accepted. I mean, okay, so what's the time and the space complexity, right? Let's see. Uh, mm, so for top-down DP, the time complexity will be the combination of the I and the mask here. So which means it's gonna be the length of the size. Uh, this is m, this is n. So the combination of this one is like the m times n. Okay, and how about here? Let's see. So here, let's say I think this is not accurate because I think the state so the top-down DP time complexity is going to be the state, the number of state plus the cost for each state. So the cost for each state is m. So this is m, right? So this is m. So we have m here, but how about the total states? The total states is that so here the first one is n, right? So we have n here, and the second one is the mask here. So the mask, the total possible values in the mask is we have 0, 0. Okay, that 1, 1, 1, 1. So the total combination of the mask is going to be 2 to the power of m. Yeah, because at each position we can have either 0 or 1. So in total we have 2 to the power of m combinations of the mask here. Okay, so yeah, so basically the total time complexity for this solution is m times n times 2 to the power of m. Yeah, yeah, that's that. And the space complexity is the is it basically is the size of this. It's the size of the state here, which is the n times 2 to the power of m. Okay, yeah. Since since we're doing like a little bit improvements here, basically if it's we're using like a real brutal force way, not a brutal force way. I mean, we could have also used another bit mask to track the statement the state of group one here. Okay. I mean, we can also do that, right? I mean, if we do that, I mean the time complexity will become what? Will become the uh 2 to the power of m plus n. Okay, right? and then times m. Okay, right? Because in that case, I mean the combination of the first property will also be a 2 to the power of n in this case. But here we're only having like n here. So basically we're improving from 2 to the power of n to n here. Okay, by only using like the index here instead of another bit mask. Okay, cool. Yeah, I think this is like a great problem. I mean, the DP in the DP idea is not that hard, but I think what I learned at least from this problem is that how we can use the beat mask uh, to mark the status of a list of the element, okay, by using an or and and, and then after that we just need to come up with a strategy of connecting all those points. Okay, cool guys. I think that's it for this problem. Thank you so much for watching the videos, and I hope you guys enjoy the videos and stay tuned. See you guys soon. Yeah, bye bye.